Good evening, everybody, and welcome to this 15th edition of the Plenty in 20 talk series of System Society of India, Thiruvananthapuram chapter. Today, we have an eminent speaker, Dr. Pankaj Priyadarshi, outstanding scientist and project director of the Advanced Technology Vehicles Project, with a very interesting topic, the No Free Lunch Theorem and the opportunities it offers. Dr. Pankaj did his BE in Aeronautical Engineering from PEC Chandigarh, followed by ME in Aerospace Engineering with distinction from IISc Bangalore, and subsequently he completed his PhD in Aerospace Engineering from IIT Kanpur. He worked as adjunct professor Aerospace Engineering Department at IIST Trivandrum during the period January 2010 till May, May 2015. Prior to that, he has worked as the division head of ACDD VSSC since his joining till July 2015. He was the group director of the ADSG VSSC until 2024 March. Subsequently, he took over as the project director of ATVP from April 2024 till date. He was a mission director for the ATV D03 dual fuel scramjet DFS mission and the principal investigator of multiple technology development projects on launch vehicle stage recovery such as IAD and drone net for mid-air recovery. He played a key role in the aerodynamic characterization through wind tunnel testing and CFD of PSLV, GSLV, LVM3, ASLV, SRE, and future re-entry vehicles, DMRJ, FTD, and RSR vehicles. He has held other positions like deputy project director in the Human Spaceflight Project and project manager of DMRJ, FTD. And his main areas of research are launch vehicle stage recovery and multidisciplinary design optimization, computational fluid dynamics, wind tunnel testing, etc. He has more than 15 journal publications and one book and more than 90 conference papers and has given more than 46 invited talks. Now over to you, Dr. Pankaj, for the talk.
So I will just start off. So, so my slide is visible, isn't it?
Yes, sir.
Yes, yes. So, very good evening to all of you, and thank you, Dr. Jayakumar, for this nice introduction and asking me to speak on this problem. It's a very interesting theorem which was introduced to us by Professor Kalyanmoy Dev in one of his courses, which I attended some 25 years back. And it really fascinated me, and it answered some of my anxieties and this thing. So today's talk is titled around this, but I would like to expand beyond that, and I would like to pitch optimization as a interesting tool for practicing scientists like us, engineers like us, and to also researchers and students who would like to enter into this field. So, with that objective, I have made this very short presentation, and I have tried to keep it as non-technical as possible. So, so keep your expectations very very mild on this presentation. So so let's first hear what is the, we have often heard this statement, there is no such thing as a free lunch. So I wanted to see where it came from, and it looks like it has come from a 19th century US saloons where they used to offer free lunches so that people could come and buy some beverages from them, alcoholic in nature, which were costly. So the phrase started coming that there is no free lunch, uh, one intends to pay for it. And later in 1962, a Nobel laureate named Milton Friedman, he popularized this phrase by putting it in his book. And he kept on saying that nothing is completely free, and every choice you make involves an opportunity cost. So you pay somewhere, you gain somewhere. So that is the uh, flavor with which this theorem also was stated. And of course, we know it very well today. Today, in this arena of social media, we know very well that nothing is free. And the saying goes that if we are not paying for a product or a service, we are that product and the service which is being sold. So I thought one nice example of this is Google Maps or Apple Maps. I hope my slide is visible, isn't it? And my mouse is also visible. My
Yes, sir. Slide is visible.
Yes, yes. So let's look at. See, we often use Google Maps, and it's very useful for people like me who keep on forgetting paths, and especially if we have to go around on multiple paths. So, for example, here some 7 stops have been identified by somebody, and a route is planned. And if this problem is given to an optimizer, that fellow can actually, find out an optimal route for you. And this 5 hours 17 minutes can be reduced to 3 hours 16 minutes if time is a cost objective. If perhaps the fuel cost is an objective, it could be a different path. But all these things can be done by optimizers, and they are being done routinely. And perhaps on a side note, I can say, we keep on seeing this red and orange marks and yellow marks indicating where the rush is. So all this information is given free to us by Google Maps and others, but actually they are using our travel histories to find where the traffic rush is there, traffic stops are there, and they use all this information to derive the optimal path so as to minimize time, fuel, etc. And this is also where no free lunch is applicable. So they are giving us this service free to use on a personal basis, but every time we book a Swiggy or a Zomato order, every time we pay 2 to 3 rupees to Google via these vendors to give them an optimal path for uh, giving us that service. So uh, we all know, and we all have had exposure to optimization algorithms. So I just wanted to say, just name a few. See, a steepest descent is one of the classical algorithms which all of us know. That is, you go in a, suppose you are trying to minimize a objective function. So you look at a gradient and go down along the steepest gradient. So all this is, well known. Of course, for ascent, you would go along the positive gradient direction. And it's one of the oldest algorithms, very intuitive, and people have worked further on it, and they have come up with algorithms which are making use of the second derivative, not just the gradient which is the first derivative, but second derivative. And they precondition that gradient vector with its curvature and get more interesting, more optimum kind of optimization algorithms. We have also algorithms like the branch and bound algorithms, which are useful for discrete or combinatorial optimization problems, like the one which we saw in the last page, where the optimal path finding algorithm is there. You have discrete choices whether to take this path, and what is the order in which we should take the paths. And these algorithms come under the combinatorial optimization or discrete optimization problem frameworks. And I think few of us would have heard this TSP problems. That is the traveling salesman problem. It is one of the very famous and very complex optimization problem. And they are tackled by these algorithms in collaboration with branch and bound techniques. On this side is little more classical algorithms, and this side is now you could call them also classical, but like 20 30 years back they were really different. in terms of evolutionary algorithms called, one of the most representative one of them is the genetic algorithms, which simulates natural evolution and employs operators like selection, crossover, mutation with many variants. And in a similar class is very interesting algorithms like simulated annealing, which is inspired by our annealing in metals. And this also can be posed as an optimization algorithm to solve problems. And of course, there are a large number of hybrid algorithms available. So I'll just narrate a small story. Some 25 years back, a few of our colleagues were going in a train for attending one meeting, and there was, we had all the free time in the world, and we were trying to discuss which is the best algorithm. And at that time, I used to work on genetic algorithms, and that used to be a fancy for me. So our one of my colleagues, a very dear colleague and mentor also in some way, he was arguing that no, adjoint methods, and in that using gradient based methods with the augmented by Hessians is perhaps the best. And it looked also logical that it is quite comfortable to go to those methods which can quickly get the results for a convex problem or for a quadratic kind of a problem with minimum time. So it looked there, but I was trying to argue out, no, if there are multiple modes, and if there are there are complex boundaries, complex constraints, this may not be right. And that time I did not know about the no free lunch theorem. And later, when I came to know, I thought this is the answer. So this was proposed in 1997. Approximately the same time we were traveling in train, and it is written by Walpart, and he has multiple papers actually. And then this particular paper he has co-authored with McCready, and he has written a couple of theorems called no free lunch theorems for optimization in a very respected journal called IEEE Transactions on Evolutionary Computation. And what it says is, so this is perhaps the, you know, this is one thing which, I request attention from everybody. For any algorithm, any elevated performance over one class of problems is offset by performance over other class. So mathematically speaking, it says that if we were to take a sum over all objective functions in the space of objective functions. See, objective functions, all of us know what they are. Objective function could be minimizing the cost, minimizing the time. It could be anything on any problem. So kindly see that we are talking about a really huge set of problems. The problems, objective functions could be from finance, could be from engineering, could be anything under the sun. So if you were to sum over all the objective functions ever existing in the world and sum up their probability of finding an optimal solution corresponding to the objective function f, and in the nth case, using algorithm 1, it will be identically equal to the sum of the probabilities for the same problem set, uh, of course, summed over a very large set of problems using algorithm A2. So it's a wonderful problem, and they have solved it using induction. They've proved it using induction, and it answers my problem, which was discussed in our train journey. All it said was code this problem, and you say I cannot claim evolutionary algorithms like genetic algorithms are best, or nobody can claim that the very mathematical sounding steepest descent with Hessians and perhaps optimally generated low cost Hessians is best, because this theorem states if you were to sum up the probabilities over all objective functions using algorithm 1 or algorithm 2, the performance is the same. And if you were to divide by number of objective functions, it means average performance of any algorithm is the same. Just to confirm, I hope I am audible and screens are visible.
Yes, 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 sir. You can go ahead.
So this is very, very interesting, but I'll leave it at this. Otherwise, I can only prove two lines in this. So as I stated, my personal favorite was and still remains multi-objective evolutionary algorithm. Why it is a favorite is because hardly anything which we want in life is single objective. After I was exposed to this multi-objective, and I see everywhere multiple objectives are sitting. And this one classical thing which we keep on seeing, and few of you would have seen this picture of in my it's couple of presentations is, let's say when we want to go and purchase a car, all of us want the best comfort and all of us want it very, very cheap. So lowest cost, highest comfort. So actually we are targeting a free car which is of first class. But in life this never happens. And if suppose we are to look at two, let's say, equivalent configurations, having same kind of a comfort level, and if the cost of one is higher than the cost of this, then we could say that this is dominating, and hence I would always choose this. Similarly, if you were to take the same cost cars, two of these cars which are same, and one has a higher comfort for the same cost, I would choose this. So all the cars on this set are called a parity optimal cars, and actually there is no way to choose one from the other. You have to bring in a third criteria to choose anything from that. So if you see anything in life we do, we involve multiple decisions. So multi-objective. And to say it mathematically, in design space represented by X design variables, there is a feasible space which gets mapped into a space of objective functions f1 to fn, and among them, if we are looking for example, a maximization of the two, then this could be an optimum pareto optimal front. Or if we could look at the minimization of these two functions, then this surface would become the pareto optimal, and it would dominate all solutions which are here, which can be traced back to the design variables x1 x2 set in this frame of reference. Now, another reason why multi-objective is favorite, no doubt, but why evolutionary algorithm or optimization algorithms are good is because when the problems are multimodal and the our steepest descent or Hessian based design or optimization algorithms, they get stuck in local minima. If they are if we use these kind of algorithms, we can get optimum solutions for uh, multimodal problems with huge voids corresponding to constraints. So these algorithms do reasonably well. And when we were Okay, so what I was saying was that when I was working on a little complex problem like a design of a re-entry module, so there where aerodynamics was involved, trajectory, heating, TPS design, structural design, etc., fairly complex system with large number of constraints and multiple objectives, we found a lot of issues. And when that NSGA2 algorithm I was using, it was giving very nice results, but there was some issue that I was not getting a steady Pareto front. And there, in the three, genetic algorithms have three operators. One operator is selection, second is crossover, third is mutation. And when I worked on, solving that problem, one idea struck me to use to modify the selection operator by putting a elitist, a separate, augmented operator, and it gave me very good results. Not to say it is much better than the other one, but to say it could be marginally better. And I could get configurations like this, which is like configurations A to F, which are of this type, which give high cross range, and configurations of this nature, which are giving me predominantly higher net useful mass, and a set This one plus this one is the Pareto set for this. And I can just show you that the performance of this optimization algorithm on a standard test set of problems called DT-LZ problems 1 to 7. It showed a pretty good comparison. Kindly see, this one is the one which is the new optimization algorithm, and its results are compared with one of the most famous algorithms called NSGA2, which has a very large set, some 10 to 15,000 or even 20,000 citations available, and another interesting, very elegant algorithm called Epsilon MEOA. We can see that it is giving reasonably good, Pareto front on DTLZ1 problem, DTLZ2 problem, DTLZ3 problem. Kindly note, even though the Pareto fronts look similar, but the test problem becomes progressively harder and it's more, involved. So DTLZ4 problem, we can see how well spread it is, and even on problems which has a degenerate, it's a three objective optimization problem, but the Pareto front degenerates to just one curve. Even on that, we can see that this fellow gives better results. But kindly note, it may be more uniform, more closer with respect to the actual the true optimum solution. But close to here, it is showing a little more spread than the first one. Even though this is least accurate among the three, but it is, giving a good solution there. Similarly, DTLZ6 gives a fictitious Pareto solutions here, and here it gives much higher spread, but the proposed algorithm here gives a much cleaner solution set. And this is perhaps the hardest of the all, and four disjoint Pareto fronts, and it gives a reasonably good solution. And if we were to quantify and look at it, we could see, at least on the hardest problems, one third lower error as compared to the true Pareto front, to as much as 2 to 3 orders better uh, RMS error as compared to other competing solvers. So all what I would wanted to just say here is that mathematical background, mathematical specialists in optimization could also come up with optimization algorithms in a fairly heuristic fashion, which did extremely well on the set of problems of interest to us. I'm sure from the NLP side, no free lunch theorem side, it would be worse in some other frame of reference, a small hint of which we could see in the previous graphs, but certainly. But even if now, a set of people are not convinced about NFL theorem and swear by only one optimization algorithm, anything we can choose, they are still welcome to use optimization, because you have a plethora of objectives to choose from. You could choose from payload minimization, payload mass maximization, sorry, or NOx minimization, time minimization, cost minimization, cost per kg minimization, reliability maximization, robust maximization. So you have a menu of objectives to choose from. You have number of objectives to choose from. Typical problems we work on today have, we would like to do 20 objectives, but understanding and convincing others about two objectives itself is difficult. So you have a choice in number of objectives, number of constraints. Actually, number of objectives and constraints can always be interchanged, and and you have a lot of choice, and optimal solutions vary a lot with the number, type, quality of constraints we choose, and the physical relevance of the constraints. Or perhaps one of the most important things, if you change your fixed parameters and swap it with design variables, it can give you another set of opportunity to come up with separate designs. For example, in our launch vehicles, if we fix the engine uh, for among the set of available engines, you get a solution which is unique for your problem. Let's say for India, that is the unique set of optimization problem, and you will be able to develop a vehicle in such a short time, more reliable fashion, with the production capability already put in place. So I would like to conclude by saying, by repeating a quote from Euler, whom all of us owe our most of our professional life to. He said, "For since the fabric of the universe is most perfect, and the work of a most wise creator, nothing at all takes place in the universe in which some rule of maximum or minimum does not appear." It means optimization is there at every place, and I, like to push for, or welcome all students, professionals, and researchers to put this also in the menu of work which you, or the tools which you have. And I would like to conclude by saying that optimization is ever expanding. Most of research happening in AI ML can be traced to an optimization algorithm or the other, and it can be applied to any area, be it in engineering, logistics, production, anything, physics, finance, design, even drug design. And NLP theorem will guarantee that researchers can endlessly do search in the design space of optimization algorithms and contribute algorithms tailored to any objective function F, any constraint type, inequality constraint type G, or any equality constraint type H, and a combination of all of that to continue to find out unique design solutions which can be competitive in the world. And we can do optimization in all the time using any of this. So thank you very much. I hope I could convey which I just wanted to convey for NLP, and a little superset of that by saying objectives, constraints, and objective functions are also and uncertainties. In fact, I forgot to tell, uncertainty is another big field which can be introduced into optimization, and wonderful results can be obtained. So thank you.